Thank you. 1 hour. Yes, so I will continue the general formalism that I started to develop yesterday. And then I will illustrate, let's say, the importance of boundary conditions and boundary terms in the very simple case of electromagnetism, but that conveys many of the important ideas, or illustrates also many of the important ideas. So the second point that I wanted to address is the question of proper and improper gauge symmetries. So I didn't talk really about gauge symmetries yesterday, and I will start then today. So I will assume that I am dealing with a field theory that has some gauge symmetry. And the question is, what is the Hamiltonian description of gauge symmetries? And the answer to this question has been given a long time ago by Dirac. And he has shown that even though the Legendre transformation is not invertible, so the standard method for going to the Hamiltonian formalism doesn't work as such, one can amend it, and in the end, one ends up with a canonical description of the system in terms of in phase space, in terms of conjugate variables. And but there are of course new features. There is some price. I don't know if it's a price, but there is something to be paid, which is that there are constraints. In the theory. And so there are constraints on the canonical variables, which mean that the allowed physical states, classical states of the system, which are described by values of Q's and P's, are restricted. They have to fulfill the constraints. So the constraints I will collectively denote by GA. And since I'm in field theory, they will depend on the coordinates. So a gauge transformation is a symmetry transformation that involves arbitrary functions of time, but also, since we are in field theory and local field theory, of space. And the corresponding constraints will depend on X. Now, the constraints actually not only, so these would be the constraint functions, and Dirac tells us that, so there are some constraint functions, and the allowed configuration should obey that equation. Now, these are also functions of the phase space variables that I have not written here. Usually I will not write any argument. Here is just that I want to emphasize that we have constraints, independent constraints per space point. Okay, but of course these are conditions on the canonical variable, so they also involve the fields, the conjugate momenta, and the derivatives up to some order. But this is not written explicitly. Now the constraints also generate, as Dirac has shown, the gauge symmetry. So I will assume that the degeneracy in the system is due to the gauge invariance, which implies some local Noether identities, and these are the only thing that are responsible for the degeneracies of the system. And so the constraints which appear in the system will only be constraints related to the presence of a gauge symmetry. And then in that case, one can show, I mean, this was analyzed by Dirac, that the generator of the gauge symmetry will take the form, and that's why people say the constraints generate the gauge symmetry. So if these are the gauge parameters, which are also a function of X, but as I told you, I will not always write arguments. You sandwich the constraints with lambda A. And well, if the gauge parameter decreases sufficiently fast at infinity, that's enough. But you might have surface term. And I will spend a lot of time analyzing surface term in the case of electromagnetism, so you will see, you will have a more concrete realization of that. But so you see that if lambda A goes to 0 at infinity so that you have no surface terms, the corresponding generator is equal to 0 when the constraints hold. Okay, so we saw an example of that actually yesterday with electromagnetism, we observed that, so if you undo the Dirac analysis for electromagnetism, so the Lagrangian is minus a quarter f mu nu, where these are the gauge invariant field strengths, and the gauge transformation are that the vector potential is the transform into the gradient of a scalar, so an exact-one form. And yes, and then you might ask, and then the conjugate momenta, as I told you, well, this clearly does not involve time derivatives of A0 because it's antisymmetric. So the first constraint you get, and Dirac called it a primary constraint because that's what you get from the Legendre transformation, is that this, now when I write this symbol, so which Dirac called weakly equal to 0, that means that this is not an identity, it's just it's an equation. So pi 0 is not identically 0 at an arbitrary point in phase space, but you have to set it equal to 0. So you have to go to describe the physical system to the surface where it vanishes. And then if you go through the Dirac analysis, you get another constraint, which I wrote yesterday, which is that the divergence of ik, momentum conjugate to ak, is equal to 0. Now, if there are charges, if you couple the system to a charged field, there would be the charge density of that charge field that would appear here. So this is really Gauss's law, since pi k, as you can show by computing it from the Lagrangian, is the electric field. We have the divergence of electric field minus the surface density, the charge density is equal to 0. Okay, so these are the constraints in that case. And if you compute the bracket of the fields with the constraints, okay, so, or if you want to more precisely, if you want to see what the constraints, I mean, what this expression generates on the field, so that expression would be in our case, well, we have two constraints, so there would be two parameters, let's call it epsilon, eta and epsilon. That would be the integral over d3x, and I will be in 3 dimensions for electromagnetism. Not because we have to be in 3+1 dimensions, but it's just because I know the formula in 3 dimensions and I will not have the reflex to write d all the time. So let me be in 3 dimensions, but there is nothing special about, for what I'm going to say about 3 dimensions. And we have so 2 constraints, eta of x, so that would be the analog of, I mean, this expression in the case of electromagnetism, plus epsilon of x times g of x, plus perhaps boundary term. And we have seen that indeed, if I look at this, so this, at least when, because I describe boundary terms, but not, I will come back to that later. So for the moment, let's assume that epsilon and eta goes to 0 sufficiently fast at infinity that I don't have to worry about surface integrals at infinity. We have seen that in that case, this is a generator of a canonical transformation. And if I compute the corresponding canonical transformation, I get that delta eta epsilon A0 is eta, because A0 is conjugate to pi 0, and delta epsilon eta ak is dk epsilon. We computed that yesterday, which I have to compare with delta epsilon A0 is epsilon 0 dot, delta epsilon ak is equal to epsilon dot k. This is the Lagrangian description, this is the Hamiltonian description. And if you recall that at a given time, so on a given space-like hypersurface, a function and its time derivatives are independent data, these two match if you view eta as epsilon 0 dot. Okay, so indeed there are two, I mean, at a given time, because the gauge transformations involve the gauge parameter and the time derivative of the gauge parameter, I have effectively two independent functions. Yeah, sorry.
Yes, it's good.
Thank you. Okay, so there is indeed, we see indeed that in that sense, I mean, one we have appropriately identified maybe, and sometimes the parameters have to be redefined and the complicate might be not entirely obvious, but you might also have to use equations of motion because in the Hamiltonian description, when you compute the bracket, you get no time derivative. I mean, that's a phase-space computation. You take bracket at equal, but in the covariant description, you might have time derivatives of the field that appear, and you have to use the equations that eliminate the time derivatives. But I mean, this is well under control, and it's already true for general symmetries in even a finite dimensional mechanical system. When you want to compare the description in the Lagrangian formulation with the description in the Hamiltonian formulation, so there is nothing more here. Okay, but so we see that the conclusion is, indeed, we have constraints, and indeed, these constraints generate the gauge transformations. Now, if we now assume that epsilon does not go to 0 to infinity, as I explained yesterday, there is a boundary term that you pick, and then you have to cancel it, and we have to amend what I said. I will come back to that later in the detailed case of electromagnetism, because also I think that to discuss the explicit form of the boundary term, well, there is, when you integrate by part, you will always get, in a sense, the same boundary term. But to discuss its explicit value, whether it's not 0 or 0, you need to know more about the explicit form of the decay of epsilon and of the fields, and you need to tell something about the boundary conditions. So there is a lot of, there are many identities that exist without knowing the decay of the field. I mean, you just integrate by part. These are called local Noether identities. But if you want to see whether a surface term is 0 or not 0, you have to say something more, which depend on the boundary conditions. And with this, I will illustrate later. Now, I want to insist that at this stage, the symplectic, you have really a phase space with conjugate momenta and a symplectic structure in that big phase space, which contains also unphysical configurations that are not solution of the constraints, as a non-degenerate symplectic structure. I mean, A0 is a conjugate momentum pi 0, and AK as conjugate momenta as have the conjugate momentum pi k. Of course, if you set pi 0 equal to 0 and you go to the constraint surface, we know that the induced the pullback of the symplectic form will be a two form that is closed but not non-degenerate. It will be pre-symplectic, and then you have to take the quotient and go to the reduced phase space. I will say a few more words about this, but at this stage, I have a well-defined symplectic structure. Okay. Now, also, as I said, so come back to the general theory. In general, the generator of gauge transformations will have this bulk expression, and then there will be a surface term. So let me be a little bit more maybe precise about the form of the surface term. It will depend on so it will be on the sphere at infinity. Of some asymptotic value. I mean, it will depend on the some asymptotic values of the field. So this is very schematically written. Some density that will depend on the fields, dd minus 1x. It's just to emphasize that there will be some non-vanishing contribution to the generator when the parameter of the gauge transformations do not go sufficiently fast to 0 or sufficiently fast to 0 at infinity. Okay. Now, one good thing about the, now I want to define an asymptotic symmetry. Now, when I will use the word asymptotic symmetry in this lecture and the next lectures, I mean two things. So it's a gauge transform. So this is gauge transformation, so a canonical gauge transformation. Well, there will be boundary conditions, as I told you, to make sense of the surface term, and we need some boundary conditions, well, to completely specify the theory, and different type of boundary conditions might actually define inequivalent theories. So that's why we need boundary conditions. So this gauge transformation should preserve the boundary condition that preserves the boundary condition. So maps allow, because when you give boundary conditions, you are also making precise what you mean by phase space. These are configurations of the Q's and the P's that obey some boundary conditions. So they should map unallowed configurations or non-allowed configurations, or they should preserve the boundary conditions, and they should also be defined by a symmetry. It's a transformation. So a transformation, it's a vector field. Well, I'm looking at infinitesimal transformation. So the corresponding vector field should be Hamiltonian. So the gauge transformation is a vector field in a sense, so is a Hamiltonian vector field. It has a canonical generator. And the only thing that this means is that it preserves a symplectic structure. Doesn't mean actually that it necessarily commutes with the Hamiltonian. Well, that would, well, for symmetry, I might add that statement, but for the moment, I'm just asking these two things. So that means that there exists, that the following equation is fulfilled. The V of internal contraction with the vector, so a gauge transformation xi, say, xi omega is equal to 0. And then we know, because it's a gauge transformation and from the Dirac analysis, that in fact, the generator, it will be Hamiltonian, and the generator will take that form, proportional to the constraint, plus a surface term. And so this condition is really the statement that there exists a surface term in such a way that that we have this, well, that's equivalent. So that's minus dv g of lambda a, in fact. Huh? Okay, but so if you have a gauge transformation that preserves the boundary conditions, but which does not leave the symplectic form invariant, so you don't have that, I will not call it an asymptotic symmetry. It will be an asymptotic symmetry if both conditions are fulfilled. Then I will be able to talk about generators, talk about the bracket of the generators, the algebra of the asymptotic symmetries, etc. And so let's talk about the brackets. Now, why do we call it asymptotic symmetry? What is it? I call it asymptotic because you see that the form of the generator tells me that the value only depends on what is at infinity. So if lambda a infinity is extended inside in a different way, the value of the generator will be the same. So it's only the asymptotic value of the transformation in a sense, which is relevant. And I will make that more precise now, that statement. So suppose that I take the bracket of two asymptotic symmetries. So parameterized by the parameters lambda 1 and lambda 2. Well, by definition, why did I put one? No, I mean, normally everyone would put 1 first and 2 second. So that is the transformation under the gauge, that would be the transformation under, so it would be the Lie derivative along the vector field associated with the second gauge transformation of the first generator. And then I can just compute. And so I will see that I will get a variation of the bulk piece and a variation of the surface integral. Now, the variation of the surface integral will clearly be, these are local transformations, will clearly be still a surface integral, okay? I will get some surface integral. But let's focus on the variation of the first piece. Now, well, I should have said that before, but since the constraints that come from the Dirac analysis for a gauge system, and I said that I was assuming that all the constraints were related. I mean, the origin of the constraints was the fact that the theory had gauge invariances. The constraints that emanate from the Dirac analysis are first-class constraints, which means that if you make a gauge transformation, starting from a point which is a constrained surface, it will remain on the constrained surface. Well, if not, that would not be a gauge symmetry, okay? If you go from an allowed configuration to a non-allowed configuration, it's very difficult to call that a redundant transformation, okay? It's rather violent, okay? Which means that the bracket of the constraints, I mean, so if you compute the variation of the constraints on the gauge transformations, it vanishes when the constraints vanish. So it will be some combination of the constraints that might involve the fields as coefficients, but it's combination of the constraints. And so it will take again the same form with some other coefficients, but it will be, so bulk, it's a bulk, I will say bulk. So it has exactly the same structure. And also we know, because the good thing of having well-defined Hamiltonian vector field, we know that this is actually, this generates a well-defined, this is a generator of a well-defined transformation. So actually the surface term is precisely the surface term that you need to make the full thing well-defined. So we see that the bracket of two generators of gauge transformations is again a generator of a gauge transformation. So the asymptotic symmetries, sorry, so to be more precise, I mean, because it's more just than that. The bracket of two asymptotic symmetries is an asymptotic symmetry. Well, it preserves the boundary conditions because if you compute if you act with a vector field that annihilates something and takes the Lie bracket of the two such vector fields, of course it annihilates, so the boundary conditions will be preserved, and it's a Hamiltonian vector field and we see that the generator is of the same type. So the bracket of two asymptotic symmetries is an asymptotic symmetry. They form an algebra.
Marc?
And you can also, someone ask a question?
Yes, from far away.
Yes, okay.
I have a question. What are the assumptions here? For example, you seem to assume that dV has no cohomology. Is it like this?
Yes, dV has no cohomology, yes.
That's an assumption, right?
In the case that I am considering it has no cohomology, yes.
Is this case here now only electrodynamics, or it's a general?
No, absolutely not. It's gravity is included, supergravity is included, or field theories which appear in the description of the fundamental forces.
Okay.
String theory, if you want, also.
Mm-hmm. Okay, and okay, thank you.
Okay, then there is something more. You can see also that if you take an asymptotic symmetry for which the boundary term is equal to 0, because, for instance, the asymptotic values are 0, the gauge parameters decrease fast enough, then, so for instance, suppose that this is the case for Z1, there's no boundary term, well, then you can see from the argument that I said that the resulting Poisson bracket will also have no surface integral. And so if a generator is weakly equal to 0, its bracket with the other generators of asymptotic symmetries will also be weakly equal to 0. In other words, they form an ideal. And since they form an ideal, you can take the quotient. And so I will actually introduce the definition. A proper gauge symmetry will be an asymptotic symmetry, which has vanishing generator, and an improper gauge symmetry, well, will be a gauge transformation for which the generator is not zero, which means, as we have seen, that the surface term is different from zero. So when the surface term is equal to zero, I will say this is a proper gauge symmetry. And when it is not equal to zero, it's an improper gauge symmetry. And from what we have seen, because proper gauge symmetries form an ideal of the algebra of all asymptotic symmetries, and what I will call the asymptotic symmetry group, or sorry, the asymptotic symmetry algebra, I mean, the group structure might have to be discussed, is a quotient. And so, which is meaningful because I have an ideal. And what does that mean that we go to the quotient? That means that two asymptotic symmetries that differ only in the bulk term, but have the same surface integral should be identified. Okay. So if you have the same value of the gauge parameter, sorry, but if you extend that differently inside, you will only differ by something that is vanishing inside, and this, you take the quotient that is to be identified. In other words, the only relevant thing are the asymptotic values of the gauge symmetries, of the gauge parameters, and this is why the term asymptotic comes. Only the asymptotic values is relevant in the end. Now, maybe I say a few more words. So what does that mean? That to take? I repeat it. So when you take the, so I'm taking the quotient only by proper. That's very important. By proper gauge symmetry. That means is a quantum theory, and that's probably the only thing I will say about the quantum theory here. That in the quantum theory, how do we quantize system with gauge symmetries? Well, there are many equivalent ways, but one way is to impose the first class constraints. So that also to ask that the physical, so you want the physical states to be gauge invariant. Actually, that's probably a better way to say it. So you want physical states to be invariant. You have to take gauge invariance into the quantum theory. What does that mean that they should be gauge invariant? Well, actually, that means that they should be invariant only under proper gauge symmetries. So they should form the trivial representation, if the trivial gauge symmetries form a group, whatever, they should not transform under trivial gauge symmetries, but they can form non-trivial representations of the improper gauge symmetries. And we are familiar with that in gravity, say. We know that Poincaré transformations are diffeomorphisms, after all, but there are diffeomorphisms that do not go to zero at infinity. And we are not requiring that the physical state should be in the trivial representation of the Poincaré group. We can have a non-vanishing mass. We can have a non-vanishing spin. These are meaningful quantities, but that means also that the states will transform when you make a Poincaré transformation, even though a Poincaré transformation is a diffeomorphism. You can boost a black hole. You can change the orientation of the spin. So this is just familiar statements, but it's very important. You are not imposing that all gauge transformations kill the physical states, only those which are proper. The other ones, they take the same form. So it's, for instance, electromagnetism, they are all of that same form, but the difference is whether epsilon vanishes at infinity or has some more elaborate behavior that I will actually elaborate upon in a second, okay? And so that means, or another way to say that, is that the generators of improper gauge symmetries are true physical observables. When you take the quotient, so you go to the constrained surface, you take the quotient by the proper gauge transformations, you will go to the reduced phase space. So we know that the symplectic structure is degenerate, so it's a pre-symplectic structure on the constrained surface. you take the quotient by the gauge transformations, you go to the reduced phase space, where you have a well-defined symplectic structure. And that is a physical, bracket. And that we have non-trivial, these would correspond to non-trivial observables, non-trivial functions on the reduced phase space. There are actually two ways to, and also we know that the brackets, because we are quotient, we take the quotient by an ideal, this passes when I take the quotient. Now there are two ways to compute the bracket of improper gauge symmetries. One, and both of them are described in the literature. One is actually to go to the reduced phase space. And one way to go to the reduced phase space is to fix the gauge, because you see, you impose the constraints. That means that you are going to the constraint surface. It's a pre-symplectic manifold. You fix the gauge, which is a way to go to the reduced phase space. And then if you have correctly fixed the gauge, you can define a Dirac bracket. The constraints, all the constraints would be as second class, and there is a Dirac bracket. And you can set strongly equal to 0 the constraints. And then the observables will reduce to what is physically relevant, the surface integrals, and you have well-defined Dirac brackets between the surface integrals. Okay? It's in practice difficult to fix the gauge, so it's better sometimes not to fix the gauge and to keep the redundancy. But that means, that you keep the redundancy and work after you have computed bracket modulo terms which are weakly 0. So you compute. So if I have to compute the bracket between two improper gauge symmetries, I will compute the bracket here. So I will compute the variation of G. But I know that terms which are equal to 0 in the bulk will not be. I can set them equal to 0. After I have computed the bracket. Okay. And so in the end, we have defined the asymptotic symmetry. We can compute the algebra, the Poisson bracket algebra of the generators of non-trivial improper gauge symmetries, and they will form an algebra, because as we have seen, the bracket of improper gauge symmetries in general is another improper gauge symmetry. It might be 0, in other words, it could be a proper gauge symmetry, but this will depend on the algebra. So in general, you would expect but you might get a nonlinear algebra. Actually, I should discuss that now. And then I will treat the example. I think I have time. So suppose I am asking the following question now, algebra of asymptotic or asymptotic symmetry algebra. Suppose I have found a complete set of non-trivial asymptotic symmetry. Suppose I have found all the asymptotic symmetries. So all the gauge transformations that preserve the boundary condition and which are also preserving the symplectic structure. Then, and I will denote them by G, some collective index GA, because you see this, the decay, when this was really, there might be, for instance, if you consider a diffeomorphism, it will contain the Lorentz. So in the case asymptotic flat case, there will be a Lorentz transformation for plus Poincaré. So really the number of parameters which are relevant at infinity will be greater than just the number of psi, just greater than 4. There will be 4 plus the Lorentz parameter. So that's why I'm using a different index. But so you have a set, suppose you have identified a complete set of asymptotic symmetries. What you know is that the bracket is an asymptotic symmetry, and since any function of asymptotic symmetries is an asymptotic symmetry a priori, what you expect is to get here some functions of the G. So it's a nonlinear algebra a priori. This is what you might get, and even if the gauge, so the asymptotic symmetries corresponding to the GA So the corresponding vector fields form an algebra. So if Lie algebra, for if XA really, if the XA is a corresponding vector field, form a Lie algebra. So if XA, XB, and since I know that I have an anti-isomorphism, so let me put a minus sign here. We know that the corresponding generator a priori, and this is will close. In that case, the algebra means that this does not depend on the G's. GC, but there could be a central charge. And I just want to comment that this can happen in some field theories. So let me first look at this case, but it's, at least in all the instances where this can happen, and that's important, it happens only when you have an infinite dimensional group of asymptotic, where these come in infinite number. Let's say we have an infinite dimensional group of asymptotic symmetries, which is maybe not completely precise.
Yes. What is the X? What are the X?
So these are the vector fields. So XA on a phase-based function is F G. This is the Hamiltonian vector field associated with the generator. Usually you look at the transformations and you look at that, and then you reconstruct G. So that's why so this is the analog of what is this? This is what I call Xi. Well, Xi X. Okay, yeah, sorry. Okay, so I will just say that it's important for this phenomenon to occur, a non-trivial central charge, that the G's here come in infinite number, because, well, they are in finite number. Usually you can find a field configuration, the background, which is strictly invariant under the transformation generated by the F. This you can rewrite as a variation under the transformation generated by B. So let's say XB of GA. The action of the vector field on the function XA, GA. And if you can find a background, so for instance, if you are looking at gravity and the asymptotic symmetries are just the symmetries of the background, so if that is the case, then by adjusting the charges of the background to be zero, you can show that if the charges are zero, you compute the variation of the charges, but since the background is not changing, that will be zero. And that tells you that KB is equal to zero because this is equal to zero on the background. So this is an equality, and these are charges that do not depend on central, so they do not depend on the fields. So when I go to the background, I evaluate that on the background, and you get KB. Now, also, to get a nonlinear algebra, which also occurs in higher spin anti-de Sitter gravity, for instance, it's important to have an infinite dimensional algebra here, to have an infinite dimensional set, for the reason that Maxime pointed out yesterday, that if I take the product of two such things, and I have only a finite number of parameters, it's very unlikely that the product of two surface integral can be written as a surface integral of a local quantity. However, if you have an infinite dimensional set, so this would be a function of the x's at infinity, such that the b's themselves are conserved. So that would correspond to the fact that you can take arbitrary values of the asymptotic on the d-1 sphere, then the product of the b's is conserved as well. Of course, and you know what is inside, you don't have to worry about what is inside because you are going to quotient that out anyway. So you might not get the product, but that is not important. What is important is what happens at infinity. And if you can somehow say that the integrand is conserved, but for that means that there will be an infinite number of conserved charge, then this structure will be preserved, and then you could have nonlinear terms. And actually, this does occur in higher spin supergravity, where you have an infinite number. I mean, you have infinite dimensional nonlinear algebras which appear. And I will give another instance tomorrow in my talk in 4 dimensions. Yes?
I mean, so if it is the exact symmetry of a background, it's clear that you cannot have K. But, so you explained that if it is an exact symmetry of a background, you cannot have K. But why is not possible to have a situation in which XBGA is different from 0 if you have a finite number of generators?
No, I mean, I'm just saying so the presence of a central charge can occur in finite dimensional systems. Huh? And I think the most familiar case is that look at the symmetries of the Hamiltonian H is equal to 0 for a system with 1 degree of freedom. So look at first at the vector fields. I have clearly dealt d by dq and d by dp, annihilate H. Now, if I look at the corresponding generator, maybe this is minus p, this is q, and the bracket is not 0. It is 0 modulo a central extension. But such instances in field theory are possible, even if you have only a finite dimensional asymptotic symmetry group, but I don't know examples. And one reason that I don't know example is that in all the examples that I know, the background Is it a question or?
I have no idea. Hmm? Jesus freaking.
Someone was upset by what I said. So to finish, so I wanted to say that in the cases I know with a finite number of asymptotic symmetries, these are usually isometries of some background. And we know that these isometries, they have to preserve exactly the background. And so they can only be in finite number if we are in the context of gravity, for instance. Okay, so actually this is what I wanted to say at the general level. And so maybe I will go back now to electromagnetism, because I want to illustrate concretely a point which is very important, which is the importance of boundary conditions in order, because we will see that what we mean by asymptotic symmetry for the same system with the same action, electromagnetism with the Maxwell action, can be very different depending on which boundary conditions we impose. And also I will show, if I have time, that if we add a non-trivial surface contribution to the symplectic structure, so which actually is motivated in the case of Maxwell under certain circumstances, we can also change, because then this relationship will involve somewhat different omega. We can also change the conclusions about what the asymptotic symmetry is. So now I'm talking about an example. And since I want to illustrate these general concepts, which are valid for other gauge systems, for gravity, or in flat space, or in anti-de Sitter gravity, for supergravity, for other systems, this is true, but I will illustrate it in the simplest case I know, which is electromagnetism. So I wrote the symplectic form yesterday for electromagnetism, and I will be in 3 dimensions when I talk about electromagnetism. And we saw that they were, so, and I will keep pi 0 and a0, so the momentum conjugate to a0, which was equal to 0. I could get rid of that, which is what Dirac did in his analysis, but for reasons that you will understand, I will keep. I keep pi 0. Everything depends on x, so let's not write. And maybe I will not always write the exterior product, the wedge product, so let's not write it, okay? Because I will forget that sometimes to write it. So, but this is the exterior product. And then I will discuss later the inclusion of a surface term, which I already alluded to yesterday, but to begin with, let's not include the surface term. I will modify the symplectic structure later. And we have 2 constraints. And we know that the generator of the gauge transformation takes the general form. And I want to emphasize that these are functions. So I put explicitly now the x dependence. This was the plus some boundary term. And I want to discuss boundary term and boundary conditions. And I cannot discuss boundary term, well, or I cannot discuss until the end boundary terms without having an idea of what the boundary conditions are. So what are boundary conditions? They are boundary conditions at infinity. So they are conditions on the decays of the field at infinity. Now, I will take, well, I'm in 4 dimensions. So 3 spatial dimensions. I know that the electric field goes as 1 over r squared for interesting solutions. So I will allow the electric field to go like 1 over r squared. So I will write things like that. And then the magnetic field, I will also assume that it goes as 1 over r squared, which means that the vector potential, I will take it to go like 1 over r. And so the leading order, I write with a bar. So the bar means that this is a leading order. And I will also, so that means that these are functions of the angle only, not of r. So functions of the angle, I will indefinitely write that as function of theta of phi or functions of the unit normal. It's the same to the sphere. Okay. Now I have to assume some. Now, as you will see, I will need to strengthen, at least with a second set of boundary conditions, I will use the behavior of pi k at infinity. So let me already do it now. It costs nothing. You see the constraints. The divergence of pi k on physical state should be 0. So I will assume now, if I compute dk pi k for a generic configuration, it will go like 1 over r cubed. So I'm also assuming that my functions are such that when I differentiate with respect to x, a function that goes as 1 over r to the k, I will get something that goes as 1 over r to the k plus 1. I mean, in other words, I don't have things like sine k to the 2000 that I should differentiate. Okay, this I exclude. Dk pi k, well, with this behavior, that's something that will go like 1 over r cubed. Well, in fact, I will need something slightly stronger. I will assume that this is something of order r to the 4th. And clearly, I'm not excluding solutions because on solutions, it has to be strictly 0. Okay, so that's a mathematical technicality that is not very deep. I could put r1 over r to the 20 at no cost. Well, of course, it will depend. I have to be, well, slightly careful because I want to be able to include charges, which I'm not writing explicitly. But the charges, I will assume that they are localized or decrease very fast as I go to spatial infinity. So, okay. Then I have to tell you A0 then by, well, I have no particular insight on A0, but I will take it to go like, let's say by Lorentz invariance, it seems plausible to take the same behavior. And pi 0, well, pi 0, recall it's equal to 0, so it's not really the partner of the electric field. Well, we know it's a magnetic field, which is a relativistic partner of the magnetic field. So it's more the partner of the Gauss constraint. And since the Gauss constraint goes as 1 over r to the 4th, I will take it to be 1 over r 4th. I mean, again, nothing is very deep here because after all, this guy is constrained to vanish. So I can take it to decay as fast as I want. This is not going to restrict physically the system. Now, these boundary conditions have very good properties. They include the known physical solutions, and they are invariant under rotations. That's very clear because I'm dealing with this as a vector. But so I'm imposing the same condition for A1 and A2. Okay, that's so rotations, translations, but also Lorentz boost. You can check that under Lorentz boosts. So in other words, under the full Poincaré group, these conditions are invariant. However, they are not satisfactory for one reason. They are not satisfactory for the following reason, that if I look at the symplectic form, and as I take the action seriously, I take the symplectic form seriously, and in particular, I want it to be well defined. Otherwise, it's very formal. And so you can see that with arbitrary...
Question, can I ask? The
Yes?
order of the AK and A0, higher order of the AK and A0 are different order, a different order of R, 1 over R and 1 over R square. Yeah.
Oh, sorry. That may be the question. Was that?
Yes,
of course, you could, but this means they could be 1 over R squared, 1 over R cubed, 1 over, okay. But it's true that I should have, or I should have written a little o, but I will only have capital O. Okay, so thank you. That's correct.
Thank you. But pi K and pi 0 had the different orders, right? 1 over R square and 1 over R force 2, 4.
Oh, okay, same. Sorry. It was not very meaningful otherwise. I'm sorry. Okay. Okay, thank you.
Pi 0 is...
So you are the only one listening, actually.
Thank you.
Okay, and here, but here it's correct. And let's see, okay. So I'm saying that...
is a pi 0 is correct? Pi 0, pi... No.
Yeah, pi 0, I'm assuming that I'm saying it was just technical. So there is nothing deep in that. But even without being deep, I think it's correct.
Thank you. I see.
Okay, but I'm saying that there is a problem with a symplectic structure because you see, pi k goes as 1 over R squared. In general, this goes as 1 over R, and I will have to integrate over 3x. So I will get some integral, which is d. So I mean, I will integrate over the angle. That's not a problem. It's the sphere, but I will have R squared dr, 1 over R cubed, which is a logarithmic divergence. That means that in general, this symplectic structure is ill-defined. And since I insisted, I told you we have to check that we have Hamiltonian vector field. We are in bad shape if the symplectic structure is ill-defined. So what do we do? Well, actually, one can do many things, and I will show to you. I will take different boundary conditions that solve this problem, but with different conclusions about what the asymptotic symmetry is. The first solution is inspired by what Regge and Teitelbaum did for gravity. I will impose parity conditions on the leading orders. Now, the electric field of the Coulomb charge has a property of being odd under inversion when I look at the Cartesian coordinates. See that that's a sphere. Electric field is like this, but here it's like that. So if I make a reflection, an inversion with respect to the center of the sphere, this goes into minus that, minus the same. So I will assume that, so that's the first solution. I will assume that A bar K, okay, and then pi bar K, so what I just said, minus n is minus pi K of n. And A K of minus n then, because it's a conjugate, it's natural to take it even. But also that if I take it even, when I compute the magnetic field, I will get something which is also odd. And so, for instance, if I look at the magnetic field of a magnetic monopole, that's fine. That's what I want. So I will do that. I I will argue that this is not. So I'm already. I don't want you to leave with a bad message. This is incomplete. This is not the good. I mean, this is consistent, but it fails to capture some interesting asymptotic symmetries, as I will argue. But let's see. Oops. Now you might say, I mean, that's because if you do that, what happens is that the leading order here will be the integral. Well, this multiplied by an integral over the sphere, which I did not write, but you will integrate over the sphere the product of an odd function with an even function. So it will be an odd function that you integrate over the sphere, which is 0. So the leading logarithmic divergence disappears, and then things are finite. So this is good from that point of view. You might say, but maybe, I mean, that looks so unnatural that you are destroying Lorentz invariance. Well, no, you can check that if you make a Lorentz transformation, this behavior will be preserved. That's preserved actually because the boosts have a definite odd parity. It's xk, I mean.
Mark?
Maybe I end. And then also these parity conditions are somehow the analog of the matching conditions that people do in null infinity analysis. They also relate things at antipodal points, which is what I am doing here. So there was a question.
Yes. Why is it consistent? Sorry. Why is it consistent with the Poisson brackets, the fundamental Poisson brackets?
Why is it consistent? What do you mean by that?
No, why is this sign change of only the momentum but not the coordinate consistent with the fundamental Poisson bracket?
Because precisely I will have the product of an odd. So in the Poisson bracket here, I mean the symplectic structure, because I will have the product of an odd function by an even function that I have to integrate.
No, I mean in the fundamental Poisson brackets.
What do you mean by the fundamental Poisson bracket?
Like that A with pi gives a delta function.
Well, I mean, first of all, I'm working with functions so you have to really write the bracket sandwiched with smooth function, and you will see then this, and with the smooth function with a definite parity, and that is consistent. You see the Poisson bracket is a derived quantity from the symplectic structure. So there are delta functions. You have to be careful with that. So I can talk about Poisson brackets of functions which are smooth, or otherwise I have to use a theory of distribution, but I don't want to go into that here. But so that's why I refrained in my whole talk from talking directly about Poisson bracket. The Poisson bracket is a derived quantity from the symplectic structure, and the symplectic structure is a derived quantity from the action principle. The action principle gives me a symplectic or perhaps a pre-symplectic structure out of which I have to derive the Poisson manifold or whatever. Sorry?
The conditions they apply to symplectic behavior.
Yeah, this is a leading order.
Structure is this one.
Yeah, so the next term, well, yeah, because you see, I will expand that in powers, and of course the next terms can have any parity, I don't care. In general, such terms will be present.
But if you have a bound with your symplectic structure, probably this should be defined.
Yes, I will talk about the boundary term in the symplectic structure later if I have time. Okay, so now I think I will move over time, so I don't know how much time I'm allowed to have by the chair.
A few minutes, maybe.
Few, okay. Well,
if it's enough, yes.
You know, sometimes few might have different meanings for different persons.
Okay, let's say 2.
It's a danger to say few. Sorry?
Let's say 2 minutes.
2 minutes, okay. Then you are a tough chair, okay. Then maybe I put the questions at the end then. I mean, maybe you reserve your question for later. I will try, maybe 2 will be difficult, but I will try to
okay, let's say 5.
quickly. 5, okay. Now I have to look at the gauge transformations. Well, and so I have to find so the gauge transformations, I know how they read. goes like this. And so I have to look at the boundary, at the gauge transformations that preserve the boundary conditions. Now, that means that eta should go like eta bar over R plus O of 1 over R. And this one tells me that epsilon should go like epsilon bar, which should depend only on the angles, plus, well, there could be a logarithm R term with a coefficient that does not depend on the angle, but this leads to difficulties with the chart, so I drop it. So this will be the most general solution that preserve these boundary conditions. But if on top of that, I have to preserve that, this is gauge invariant, so this does not give any condition on the gauge parameter. I see that epsilon should be such that its gradient to leading order is even, which means that epsilon bar, theta phi, should be a constant, because that, of course, drops from the gradient, plus something which is odd. So the gradient of something which is odd is even. Yeah, maybe I should write it like this. So a constant, so it's a zero mode of epsilon. So the epsilon bar can see if I develop in spherical harmonics. No, because the decay of O1 is O of 1 over R. Okay, that's why it's shifted it's pushed, by one. So. Okay.
Of R squared.
You see the irrelevant terms, I tend not to be too careful. Thank you.
Mark, since you answer, you can have more time.
And this is probably R squared.
You can have more time because you already answered questions.
Okay.
10 minutes or whatever.
Maybe someone should ask me a question, which is precisely what I want to say on the blackboard. Okay, so then I need to compute to see whether I have a well-defined variational generator. So well, I wrote it here. Huh? Now you can see that if I take dv of g, so this I can write, d3x beta e by 0 plus this, we did the computation yesterday, minus dk dv by k plus dv of the boundary term. And this I want to compare with the internal contraction of the symplectic structure with the vector field, which is defined by that. And you see that I will write it here. Under the gauge transformation defined by this omega, I get d3x. So pi a does not transform. But here I will get a minus sign because I have to pass through the first conform. Then I get minus dk of epsilon, and there was a k here. And then I get same thing with a minus sign for the same reason. dv by 0, eta. Okay. And if I compare this with this, well, I find that there is no problem with eta. So it's correctly, this term is correctly generated by that. But here I should, to match the expression which is there, I have to integrate by part. So this is minus dk of the whole thing plus dk epsilon dv by k, which matches now that recall there is a minus sign between the, and then, but I have a surface term. So I know that the integral over d3x eta, sorry, this one is the easy guy. So the surface integral over the two spheres at infinity of d sigma k epsilon by k, which is dv by k, minus plus dvb should be equal to 0, okay? So the surface term should, I mean, I should have a strict equality between this and that, not an equality up to surface term, which means that since there is no surface term here, I should have no surface term here, and everything then will fit, okay? Which tells me that the boundary term that I have to add is the integral, because it's easy to see that this is exact, and it is just e2 sigma k. This was a line element. Sometimes I write it with sigma, sometimes with s, but since it's sigma, I write sigma on the two sphere at infinity of epsilon pi k. It's a flux of the electric field, but there is in the integral an epsilon, and it's the asymptotic value, which will be the only relevant thing. Because this goes like r squared, this goes like 1, and this goes like 1 over r squared. So it's only the leading piece which is relevant. Okay. Now, and I will have to be quick for the conclusion. I will tell you qualitatively what happens. You say, oh, but that's, I recognize that's the flux of the electric field. But then I have to, epsilon bar takes this form. So there will be two contributions. Epsilon bar 0, the 0 mode, and then the rest, which is odd. Which is odd, because that's the only thing that there is, I told you. Huh? Well, there is the same thing. Huh? Pi bar k, it's again pi bar here, a d2 sigma k, okay? So, okay, now, however, because of the parity condition, so the electric field in Cartesian coordinates is odd, but that means that the radial component of the electric field is even. If the radial component here is the same as the radial component here. So, because d by dr is even. So that means that I have here an even function, which means that I'm integrate here over the two sphere an odd function, which means that this is 0. And I told you proper gauge symmetries are gauge symmetries which have a vanishing generator. So we conclude from this analysis that with this set of boundary conditions, the only proper, sorry, the improper gauge, the only, I mean, when I take the, I have to take the quotient, well, by all the etas, because the etas have no boundary term going with them. I mean, there is no, eta does not appear in the boundary term. So all the eta gauge transformations are pure gauge, proper. And then everything in epsilon is proper except the 0 mode. So I get one single conserved, I mean, a charge, non-trivial charge, and that describes a global U1. So with this set of boundary conditions, I get as asymptotic symmetry, well, with something which is rather disappointing because of what we know of the analysis at null infinity, which is a single U1. So let me just say in words how it goes, how one can improve this. Well, one can improve this and get the full angle-dependent U1 symmetry at infinity, like in the null infinity treatment, and actually one can then show that there is match between the two analyses. Following the following reasoning, maybe these boundary conditions are too strict. Why could they be too strict? Well, I think the boundary conditions on an electric field, which is a gauge invariant quantity, I mean, that's something. But to say that the potential, vector potential, which is not invariant under gauge transformations, is odd, is even, sorry, is a statement which in a sense is rather restrictive. We should say that it is even up to a gauge transformation. So we should allow, when we make a reflection, an inversion, a gradient term. And this gradient term could have a component which is even, a component which is odd. But you see that if you start allowing such a gradient term here, the constraint that the epsilon bar should be odd disappears. I could allow a gauge transformation with the opposite parity in this term here. And these are precisely the improper gauge transformations. So if I enlarge the boundary conditions by including an improper gauge transformation here, well, it will reappear here. And I will see that when epsilon bar is even, I get a non-vanishing charge, not just a zero. There is more than the zero mode. And so in a sense, we don't see the full U1 because we have improperly fixed the gauge. But I told you, don't fix the gauge, don't fix improper gauge symmetries. You are not allowed to. They change the physical state of the system, only fix proper gauge symmetries. So we should allow here a gradient term. Now you are going to tell me, but this only gives me half of the angle-dependent U1 symmetry at infinity, since I would still have the result that the odd part of epsilon does not contribute to the charge. Well, you get the other half, and this is something I will not have the time to explain, because actually, as soon as you enlarge these boundary conditions in the way I described, you find that you should allow for a surface term to the symplectic form. I mean, this is not Lorentz invariant in the sense that it is it's invariant under Lorentz transformation, but you start having problem with the boost not being canonical transformations. And this is because actually one forgot a boundary contribution to the surface, to the symplectic structure, which involved precisely A0. And because it involved A0, you will get a non-vanishing contribution to the other generator, which is precisely of the opposite parity, and the two combine together to form the angle-dependent U1 that people have seen at non-infinity. So the moral of that, I'm sorry I had to hurry in the last minutes, is that the group of asymptotic symmetries depends on the boundary conditions. Well, we have so many other examples that probably it's an obvious statement for many of you. We know, for instance, that for higher spins gravity, SL3, which subgroup SL2 I take will lead to different asymptotic symmetry algebra. So there are other cases where this is well appreciated, but this is also true in 4 dimensions for electromagnetism. And also just surface terms in the symplectic structure. Well, this actually I illustrated a little bit yesterday, the computation might also have an impact on the analysis of what you mean by proper or improper gauge symmetries, and then in the end on what you mean by asymptotic symmetry, true physical asymptotic symmetry algebra. So thank you, and sorry for the being over time.
Thank you very much for the lecture. Question, comments? Yes.
Okay, I don't know. Yes, it's a very general question. So as you explained, there are mostly two approaches. The first one was to quotient by the trivial symmetries. The second, go directly to reduce phase space and work in a gauge fixed approach. So we know we don't have a recipe for losing, history has taught us we have lost many physical observables, but if you had to come up with a recipe, what should be the approach? Would be a mix of these two things, or?
I think, I don't know. I think one has to be opportunist, depending on the system. To fix the gauge, it can be very complicated for systems like gravity. And to construct explicitly observables for gravity, I mean, it's a hard question. And I would say that the only observables that I know are these asymptotic charges when it's asymptotically flat. So I don't think that I don't have a general strategy. I think one has to look at both and keep them in mind and see which one is more suitable for the problem at hand.
More questions?
Question concerning, so at least naively, I could start from Maxwell action, interpret A0 as a Lagrange multiplier, and that enforces directly the other constraint. But then, I mean, is it possible to work like this? Because you said that you really need A0.
Actually, yes, this is how we started, I can tell you. And then we saw, well, this is consistent with this strict approach. But if you enlarge the boundary conditions by rolling the surface term, and you don't work with A0, or it's as a phase space variable with this conjugate momentum, you run into a difficulty that the boosts preserve the boundary conditions, but are not canonically generated. They don't preserve the symplectic structure. If you compute the variation of the symplectic structure without that, with these more general boundary conditions, you find that there is a surface term, which is not zero. And it will be zero only if you go back to the restricted boundary condition, but then you lose the angle dependent you want. And so initially we put by hand some what we call surface degree of freedom. And this surface degree of freedom, we realized it was the asymptotic value of A0, which would have kept me for that reason now. A0 is pure gauge, that's true, except for its asymptotic value. But of course, if you have a field, that means that two field configurations of A0, which coincide at infinity, so which coincide for this term, and if they're here, should be taken as identical. But that's the only thing that you are allowed to take a quotient by. Shifting A bar 0, what we found at this order, was an improper gauge.
So this means that they are not equivalent, actually. So if you have boundary conditions, it could be dangerous even with operation of interpreting something directly as a Lagrange.
And of course, there might be some other constraints like Lorentz invariance. And that's, if you say, I don't care about that, and there you see very clearly that they are not equivalent. One is just not Lorentz invariant, period. There is, because Lorentz transformations are not canonical, do not leave the symplectic structure invariant.